Hi, so yeah, as they said, I'm Ali. I'm the R&D manager here at Telerix. I'm going to speak to you about Telerix's technology, WellReady, and what work we've been doing about it, using it to preserve organoids and 3D culture. So just to kind of go through what I'm going to talk about in the presentation, I'm going to give a brief introduction to Telerix and the technology and the science behind it. Then move on to WellReady and kind of go through the process and sort of handling of it, and then go some of the 2D models that we've done for it, and then move on to sort of the main reason why you're here for the organoids. So just a bit about us. We at Telerix, we offer an innovative approach to the storage and transportation of biological products such as fresh cells, tissues, and viruses. So we take the approach to treat cells as the fragile, sensitive, living entities that they are, and we use alginate hydrogels to encapsulate these biological products and give them and offer them protection from biochemical and physical damage, whilst retaining viability and function without the need of harsh storage methods such as cryopreservation. As I mentioned, this is an alginate-based hydrogel, so it's derived from seaweed. And all the alginates that we use are a pharmaceutical grade that have been highly characterized and are consistent. In terms of optimization, we have optimized several formats, including in tube preservation, in plate, which is what I'm going to speak about today with WellReady. And for larger scale, we have a bag format. We've also optimized for different biological samples. So even down to the grade of sometimes we have different, say, WellReady products for different cell types. So we have a special one for neuronal cells and a special one for cardiomyocytes. And the protocols that we've developed for these have been streamlined to make the encapsulation process easy and rapid and scalable process to offer quick and effective protection for your samples. And then when it comes to releasing your samples from this encapsulation, from this preservation technology, simple, easy to use, quick, and uses a cell-friendly salt-based buffer. Just quickly a bit about the science behind this. Telerix technology relies on hypothermic preservation, so temperatures below physiological temperatures, and this slows down enzymatic and metabolic processes within the cell, sort of putting them into a sleep or pause of the cells, suspended animation. And it is in this state that allows us to safely ship and preserve these models. Normally what occurs to cells when you reduce the temperature to hypothermic temperatures is you get damage of the lipid membrane, so you get protein deconfiguration, pore formation, and ultimately this damage leads to cell death. And through the encapsulation of these biological materials in our hydrogel, that offers the protection to the membrane, and thus that's how we extend the shelf life of these biological products. When the sort of preservation time or the shipment of your biological product is being achieved, you can then easily release them from WellReady, as described before, using a salt-based buffer, and can return these cells or biological products to standard or normal culture conditions. And this is where these cells will reawaken, and then you'll end up with a model that is essentially in the same state as it was when it entered storage. Listed on this diagram here are some of the cell types that we have successfully preserved using our technology. So this is just some of them. This is not the full list. So if you have a cell model that you don't see on this diagram here, then please get in contact with us and we'll let you know if we have any experience with handling those cells and our technology. So in terms of WellReady, the product that I'm going to speak about today with organoids, it's suitable for their top cells, organoids, microtissues in multi-well plates. So we currently offer this in 24, 48, 96, and 3 or well plates. And essentially how this product works we layer the well of these plates with different alginate hydrogels. So I can go through each of the layers and what they contribute to the product. So the first layer, or what we call gel A, is a cell protective layer. So this is going to be in direct contact with your cells or organoids. And this is what encapsulates the model, offering that biophysical protection. The second layer, or gel B, is a shock absorbing layer. So this layer is used to protect the cells essentially from any mechanical disruption that may occur, say during shipment. If you are to ship your models out, sometimes couriers may not be the most gentle of handed people when dealing with parcels, so this should protect them from any undue stress. And the final layer, what we call gel C, is the sealant layer. So this essentially acts as a plug for the well. In terms of what the process is for carrying out this encapsulation, it is as simple as the diagram on the bottom right there is. You have your cells, which you remove all your media from. You then layer gel A on top of the cells or organoids. You then layer gel B on top of gel A, add a gelation buffer. And once the alginate has gelated, you give the cells a quick wash to remove any gelation buffer, and then remove the wash and the residual gelation buffer, and add gel C on top of this. And once that's fully gelated, you can then seal your plate and they are ready to ship out. Once it's reached its destination, or once you've finished preserving your cells using WellReady, again, mentioned previously, it's a simple dissolution step where you just add the dissolution buffer onto the well, remove the gel that will have turned into a liquid state, replace the media in the well, and return to standard or normal culture conditions for downstream processing, whether that be endpoint assays, any analysis, or simply returning the cells to culture for expansion. So I'm going to go through a few of the 2D models that we have looked at, particularly some of these more fragile models, more complex models. The first of these being primary human airway epithelial cells. So these are primary cells which are a bit notorious for being sensitive, fragile, and have a limited expansion capacity. For this experiment with WellReady, we were able to preserve these cells for 7 days at 4 and 20 degrees. So you can see on the graph on the left, if we look at, we're essentially looking at cell metabolic activity as an indicator for viability. And if we look at the 4 degrees and the 20 degree bars, you see that they are essentially the same as our non-stored bar. So our non-stored is essentially the cells before they have been encapsulated in WellReady. So after 7 days, we essentially get the same metabolic activity out of these cells. This can be visualized quite nicely by looking at live dead imaging. So here we have the green cells being live cells and any red dots being essentially a dead cell. And we can see that from the top panel, our non-stored cells are quite viable, they're happy, and that's comparable to the picture on the bottom right with the cells in WellReady that have been preserved in WellReady for 7 days and then returned to culture, and they are essentially similar. Whereas if you were to just leave them in normal media at this temperature, you start to see fewer cells, fewer happy cells, and you wouldn't be able to continue with that model. Second model I'm going to go through is the human iPSC-derived cardiomyocytes. So again, these are done in for 7 days at 20 degrees. Graph on the left, again, is showing viable cell recovery, where we can see that those stored for 7 days in WellReady are essentially the same as those that have those non-stored cells on day 0, and again can be visualized through bright field and live dead staining, where you can see that they retain their viability and morphology. These cells, being cardiomyocytes, they should beat in terms of their function. Now this worked last time, so we've had our technology scare, so hopefully we'll be able to see that after 7 days, they were able to retain their beating capability. showing that these cells retain their function as well as just being viable and retain morphology. The last model I'm going to go through is iPSC-derived neuronal cells. So these were stored using WellReady for 3 days. And in this 3-day period, the plates were shipped between 2 sites. So 2 trips, one there, one back. And then viable endpoint analysis was carried out. Again, graph on the left, viable cell recovery, we can see that WellReady and non-stored are very similar, whereas just having media in the wells and shipping them, you can see that you lose around 60% of the viable cells. Again, can be visualized looking at live dead staining, where you see that non-stored and WellReady are very similar, whereas those in the media, the cells have either been sheared off or have just simply died. So why are we looking at organoids to be preserved using WellReady? Well, the use of organoids is for disease modeling, drug discovery, personalized medicine has become increasingly popular recently, trying to phase out animal studies and move closer to physiological relevant in vitro assays. As these organoids are becoming more complex, they essentially it comes with a higher fragility. And it's this fragility that makes some of these models unsuitable for cryopreservation and can restrict the ability to distribute these models from the site of origin and manufacture to essentially endpoint users, which can restrict businesses' ability to grow commercially. Another issue that is being faced by these increasing complex models is that the process to generate and maintain these organoids can be quite complex. Having learned firsthand, having never really used organoids before, testing them with WellReady, sometimes getting the hang of it is the first big step. And a lot of, say, drug companies who want to just simply throw their drug onto a model and get their answer, they don't want to put in the resources into getting the technical awareness and skill in developing these models if they can just simply get an assay on their doorstep and then they can carry out their assays. It's a point of convenience. So what we looked at Telerex, we have used commercially available mouse iPSC-derived organoids. So we have looked at intestinal organoids and hepatic organoids. So we've selected these ones based on the available literature and data from the supplier and have cultured them essentially following their recommendations, which in this case is in Matrigel. Once these organoids have reached a high enough number, high enough count, size and maturity, we've encapsulated the organoids using WellReady and stored them at room temperature. Following the period of preservation, we have released these organoids from WellReady using the dissolution buffer and returned them to culture before doing any endpoint analysis. So essentially we've been looking at viability and function. And then this data is compared to our non-stored controls. As with our 2D, we're looking at the cells before they've gone into WellReady. So this is the first set of data we have, which is looking at viability. So we've used an ATP-based luminescence assay, quite standard for organoids, I believe. On the left is our intestinal organoids, which you can see here. There's a little bit of a dip, but you can mostly viable in comparison to the non-stored controls. The liver organoids on the right, we've been able to extend their preservation for longer, up to 5 days. So we preserve them for 5 days in WellReady and then return them to culture for 3 days. And you can see that the ATP luminescence is similar between 5 days and the non-stored. Again, these non-stored are also in culture for 3 extra days. The 3 extra days I'll go into a little bit why we've chosen that endpoint in slide 2. Again, just to visualize what we've seen using live dead staining and in this case using bright field as well to look at the morphology and the 3D structure. These are organoids. We want to be able to have this 3D structure being retained. And we can see that both the intestinal and the liver organoids retain this structure, morphology, and live cell distribution. In the case of the liver organoids, we went a step further to look at the function of these. The first thing we looked at was the marker expression. So we went to the data and literature that the supplier had of these organoids and selected a marker, in this case cytokeratin 19. It was highly expressed in their data, so we chose that, and we can see that the expression is comparable with the non-stored to the day 5 WellReady organoids, showing that they essentially retain this expression. And it is also comparable to the data that was provided by the supplier. The little points of intense expression is actually where the organoid is folded over during the processing for staining. But certainly more importantly from my point of view is in terms of liver organoids is their drug metabolizing capability. If you were doing drug development toxicology, these models need to have essentially drug metabolizing enzymes. So to look at this, we used a luminescence-based assay that looked at cytochrome P450 1A2 activity. And again, like with viability, we can see that this CYP activity is retained 5 days after WellReady storage and 3 days of being returned to culture. Yeah, this is comparable to non-stored, so just showing that you're retaining one of the core functions of this organoid. So the reason why we've gone for 3 days in culture, we've found that different cell types have taken sort of different times to return to their normal physiological conditions. In the case of liver organoids, it takes a while for them to regain their drug metabolizing capability. From what we've seen with CYP1A2, if it was there for 24 hours, it's actually a little bit less than the non-stored control, but eventually it does recover its activity, so can be used as essentially as if you were to have done it 5 days prior. And that's essentially the data that we have for our internal side. In terms of what we know of that other people have done using our technology, we know that some people have used WellReady and one of our other products, TissueReady, to preserve brain organoids, liver organoids, and retinal organoids. So we know of them, to name a few, that we have successfully been able to prolong the shelf life for. So hopefully the experiences of our people and what we've done internally has shown that organoids can be preserved using WellReady to retain a high viability, metabolic activity, morphology, and function. And this provides the capability to use WellReady to store and ship complex 3D organoid models at room temperature. Sort of why use WellReady, what advantages does it bring, kind of loops back around to the question we asked earlier, why were we looking at it? Well, if we use WellReady with our organoids, we can enable the shipment of complex physiological relevant cell models in an assay-ready format. You are removing that complexity that end users may not want to have, and essentially drug discovery, throw a drug on, endpoint, brilliant, simple. Increased quality and yield of cells, we're showing that in the 2D models as well, that we can provide viable and functional cells. Enhanced flexibility of workflows. I'm sure we're all aware of delays during experimentation and in a lab. If you can essentially pause your cell model, it gives you a little bit more flexibility without having to lose resources and lose time. Increased global reach, preserving the shelf life of these biological products. So essentially you can reach as far as you can get with them in that time frame. And if you can extend that time with WellReady or one of our products, you're extending that global reach. And with that shipment comes a reduced requirement for expensive complex shipping methods such as dry ice, and arguably this could be seen as safer and greener, and some countries actually have started to restrict the use of dry ice in shipments. So I want to say thank you for listening. There is going to be a white paper that will go onto the socials, and I think Lindsay's going to email it to attendees. That just kind of goes a little bit more detail about some of the data that we've shown today. WellReady is available to purchase on webshop. I would recommend, if you are thinking about using WellReady, if you get in touch with us, we can recommend the format and duration that you may expect to get with that certain cell type or model, and maybe suggest temperatures and other things to consider. So for that, I'll thank you, and I'm happy to answer any questions where I can.